Hi everyone, my name is Rotem and this is my talk, Avoid Toll Roads, Deploying Declarative Database Schema Changes. So a bit about myself, I'm the CTO and co-founder at a company called Ariga. As part of my job, I'm the maintainer of two fairly large open source projects. One of them is called Ent. Ent is a Linux Foundation-backed entity framework for Go, and Atlas, which will be the primary topic of our talk today. So Atlas lets you manage your database schema as code. We open sourced it in 2021. It's used by thousands of projects on GitHub, and it has been sometimes called a Terraform, but for databases. And I hope that by the end of this talk, you will understand why. Okay, let's begin our story by presenting our hero, which is your database. So a few fun facts about our hero. First is that every application has one. If you're writing a backend application, chances are you have some database backing it. Your database contains the application state. Containers and application versions come and go, but your database is the one stateful component that contains the application data. The database always has a schema, even if you're using a NoSQL database. That's debatable, but we're focusing on relational databases today. Your database has some schema that reflects your application data model. If you're building an e-commerce application, this data model has things like products and categories and invoices. And these models are reflected in the database tables and columns. Number four, as your application evolves, so must your database schema. When you add new features, you add new entities, you create new relations between them. These changes must be somehow reflected in the database schema so this information can be stored and persisted and presented to users. And number five, if you mess up evolving your database, you're in big trouble. Sure, you can throw away your production database and start up from scratch, but your CEO will most likely not be very pleased. When Ariel, my co-founder, and I started working on Atlas, the modern database schema management solution, we noticed this gap, even a disconnect between all of the modern things that we had with infrastructure as code and modern DevOps tools and the state of the art of whatever was available for managing our databases. Evolutionary Database Design, published May 2016 by ThoughtWorks, is still considered by many the seminal piece that defines the industry best practices when it comes to managing database schemas. When presenting the topic, I want to go over some important parts that define the current state of the affairs before we start to question them and see if we have better alternatives. At the time this paper was written, it was still a very common practice to manage database schema changes manually, kind of outside of the deployment and automation pipelines that organizations started to develop. This is, of course, completely out of line with the whole DevOps philosophy of automating things and building CI/CD pipeline. And so this article prescribes that we represent every change to the database as a migration script. This script needs to be version controlled together with the application code changes. Now, having our code repo as a single source of truth for the application is great, and storing the changes to the databases SQL scripts in our repo is a huge improvement, but that is still not enough for building automated pipelines. We need a few more things. One is that each migration needs a unique identification, basically a version number. We need to track which migrations have been applied to the target database so we don't try to create the same table twice. And very importantly, we need to manage the sequencing, the order in which these migrations are applied. Databases, being stateful creatures, require us to first create the column before we create an index on it. It doesn't make sense to create an index on a column that does not exist yet. Therefore, the sequence, the order really matters. Now, to solve this problem, many tools were created. There are hundreds of migration tools out there today Some of them are ORM specific. They come with your application framework. Some of them are language and framework agnostic, like Atlas, but all of them work in a very similar way. Everything starts with you defining your migrations in something called a migration directory. Each file has a version number. Very commonly, we use a timestamp because times increase, and so newer scripts will have a higher version number. After that, we need a migration tool. We need some tool to manage to apply these migrations to the target database. The way the tool does this is when it's applied, it reads the migration directory, it connects to the target database, and reads something that is called the changelog table. This is a metadata table that stores information about which migrations have already been applied. Once it has that information, it can determine if new scripts need to be run on the target database. And finally, at the end of execution, the metadata table, the changelog table, is updated again to reflect the current state of the database. As I mentioned before, when we started working on Atlas, we noticed this huge gap in the world of schema management. On one hand, we had tools that delivered experiences like Terraform and Kubernetes. And on the other hand, we had all of these migration tools that operated in a very different way. Now, when you think about it, the gap or the difference really boils down to a different paradigm: declarative versus imperative resource management. If we think about migration tools, they follow an imperative mindset, meaning we provide the tool a plan, a set of SQL commands to run on the target database. The tool's only responsibility is to inspect the changelog table, look at what scripts need to be run, apply them on the database, and update the changelog table. With declarative tools, tools have much more responsibilities. For example, with Terraform, we provide the tool the desired state, what we want reality to look like. The tool's responsibility is to inspect reality, to inspect our production system, for example, our AWS account, to calculate the diff. What is the difference between the desired and the current state? To turn that diff into an execution plan, and finally to run it to reconcile the difference. Okay, so which approach is better? Let's try to answer with a metaphor. So, my current state is that I'm in the comfort of the Ariga office, but my real desired state is to be some 4 kilometers west from here at Banana Beach. So the way to reconcile this is by driving there. If you started driving before navigation software was available, you will totally get the following example. So using navigation software like Waze or Google Maps is like the declarative approach, right? I have my current state, I have my desired state, I feed this into a tool, the tool inspects reality, traffic conditions, the map, the different streets, and the tool comes up with a plan. Whereas the imperative approach is like when my dad used to prepare a handwritten note for me with instructions how to get from point A to point B, which he calculated using his map book. So head west to the street, turn right on that one, after 200 meters, turn left, and so on. So I ask you again, which approach is better? We built Atlas on the declarative model, so obviously we have an opinion here. I want to list some of the benefits of using a declarative model. So first of all, if it's not obvious from the example, there is way lower mental overhead when you let a tool do the work of planning for you. It's just easier. Because it's easier, it's also faster, right? I don't need to open a map book to look at the streets, to listen to the radio, to think about traffic condition, about different hours of the day. It takes less time to use an automated tool for planning than to do it by hand. And next point really depends, but assuming that the automation tool, the automated tool, was written by domain experts, their domain expertise can be codified and turned into software so that everybody can enjoy their knowledge and industry best practices. Finally, because the declarative model offers a closed control loop, meaning it's connected to reality, the plan that will be output from the difference between the current and desired state depends on reality. For example, traffic condition, any road construction work will inform the result of a declarative calculation. Whereas if the plan is pre-computed, it might not be relevant and it might even lead us to a broken state. With the introductions behind us, let's now show a quick demo of what declarative database schema management looks like in practice. Now, Atlas can be run in many different ways. It's a standalone tool, it's a Kubernetes operator, but since we are today in a HashiCorp event, I thought it would be appropriate that we present the Terraform provider. So let's look at this very simple Terraform module. We have installed the Atlas provider. This is a provider that lets us manage database schema as part of our infrastructure as code setup. We are using a local SQLite database just to simplify things. In practice, you would be running against a MySQL or a Postgres database, something running on your RDS, but we are also seeing teams actually using SQLite for production applications. The next block is a data source that loads the desired state of the database from a SQL file. You can see that this simple created table statement represents the desired state of the database. Now, we can use many different ways to define the desired state of the database. We can use plain SQL. We can use Atlas BDL, which is an HCL based language, configuration language for defining database schemas. We can pull the desired state directly from your application framework or ORM. But for simplicity, let's just focus on defining the schema in SQL BDL statements. Next, we define a resource that binds between the database that we are managing and the desired state of the database. Let's first delete this existing SQLite file just to reset things for our demo. And now we can run Terraform live. Now, Terraform will calculate the difference between an empty database and the desired state. And you can see that it prints both an HCL representation and the create table statement that it's going to run this target database. Everything ran fine. And so when we run Terraform apply, we can see that no changes need to be made. Now let's see what happens when we add a C3, another column to our database. We can run Terraform apply and see that now Atlas wants to run alter table to add this column to our database. Again, if we rerun this thing, the state is already synced, so no changes to be made. So let's just recap how declarative schema migrations actually work. When Atlas runs with the schema apply command, or what you just saw as the Terraform provider, it starts with the desired schema. This desired schema is provided by something called schema loaders. Atlas comes pre-packed with a bunch of these that allow you to load the desired state of your database in a bunch of ways. It can be a connection to a running database that already has your desired schema. It can be a SQL file like we've shown, and it can also be code from your ORM directly read into Atlas. Once we have the desired schema, we connect to the database and we inspect it. Basically, Atlas runs a bunch of queries against the database information schema to build a representation of the current schema of the database. Once we have a current state and a desired state, we can calculate a diff. The diff basically is the delta, the difference between the two states. Now, this is not yet enough to execute because, as we mentioned before, the order in which Atlas is going to run these commands against your database really matters. So Atlas employs a bunch of algorithms like topological sort to get all the dependencies in the correct order and finally apply them to the target database. Sounds great, right? Well, as we were working on initial versions of Atlas, we had kind of silently open sourced it. It wasn't really ready for release, but then something happened, and that was that we accidentally hit the front page of Hacker News. Now, if you've ever been on this site, you know people there are very enthusiastic about software engineering, and they have very strong opinions. Some of the feedback we received was really, really positive, and we got our share of harsh criticism. I want to share with you one bit that particularly influenced us, and here it goes. So Redact 207 says, I'll never be comfortable with any tool that automatically generates schema changes, as I'm just never sure at what point it decides to delete parts of my production database. Now, this to me is scary stuff. And I don't know who you are, Redact 207. Maybe you're watching this conference today with us. We take these safety issues of managing production databases very seriously. And from this point on, in this talk, it's going to be all about how we can preserve the benefits of the declarative model while avoiding the risks and the dangers that comes with managing someone's database automatically. So how do we do that? Let's see. Let's continue with our navigation metaphor. So in Israel, we have a very famous road called Road 6. Road 6 is a very fast road. It's well maintained. It's a highway that crosses the country from north to south. When you're planning a trip, you might want or not want to drive on it, depending on your budget, depending on your schedule. And for this reason, navigation software lets you make choices to define policies of how to get from point A to point B. Declarative workflows work amazingly well for stateless resources. With stateless resources, it does not matter. You can throw everything out, spin it back up fresh, and it will still work. With your database, it's not so simple. Going from point A to point B, sometimes there are multiple ways to do it. Some of them involve locking a table. Some of them involve breaking the contract between your backend application and your database. Some of them involve losing data. So if we want to adopt a declarative workflow for managing our database, we need strategies to mitigate these risks while maintaining all the benefits of a declarative API. How do we do something like avoid toll roads that navigation software does for database management? Let's see. The first strategy I want to present is something that we call automatic migration planning. In this workflow, we take the good part of declarative schema management, which is we have a desired state and we have Atlas to automatically plan the migrations. But the output is just a classic migration directory that we can commit to our Git repository, we can review in code review, and we can even run some automation, as we'll show, to verify that changes are safe. So many teams still want to keep the version migration flow, but they want to enjoy the good part of automatic migration planning. The next demo will show how Atlas can be used to automatically maintain the migration directory of your application for you. Let's see how this works in practice. So like before, the desired state of our database is described in this file, schema.sql. But what we're going to do now is we're going to use an Atlas migrate command to calculate the diff whenever we change the schema. So initially, we don't have a migration directory, and Atlas will just write this initial migration to bootstrap the project. But now, whenever we modify the desired state, for example, we create another column, we can generate a new migration. If we want, for example, to create a new table, create table T2, we can rerun the command to generate a new migration file. Of course, if we have no changes, Atlas will detect this and tell us that no changes are to be made. Now, the advantage of this approach is that we can now add these migration files, these automatically generated migration files, to our pull requests to have them code reviewed, to have them checked into source control. So a team has ultimate control exactly what SQL commands are going to be run on the production database. If these files are added to pull requests and reviewed by humans, then of course it's possible to catch dangerous things like accidentally introducing destructive changes. But wouldn't it be great if we could just integrate this as a check in our CI pipeline? Wouldn't it be great if Atlas could do the migration reviews for us? Well, Atlas had another command called Atlas migrate lint, which can be used exactly for this. So let's now do something. Let's plan a destructive change. So let's drop our T2 table. We get this fourth migration that does drop table. And now let's show how we can use Atlas migrate lint to check the latest change. We can see that this file, this new file that we just created, contains a destructive change. Now, this tool can be integrated into your CI pipeline to prevent pull requests from landing that accidentally contain dangerous changes. You can see here by this red X that the status code of this command is not 0, meaning in a CI job it would fail. But what if we want to stay within the bounds of a real declarative workflow? Well, the next strategy is called diff policies. And this is how it works. Diff policies modify the generated execution plans based on user-defined policies. For example, a diff policy can tell Atlas to always create an index concurrently or to never drop a table. This has the benefits of avoiding the types of changes we don't want in our system. For example, to enforce that we only perform additive changes, or that we never create foreign keys, because that doesn't work in our system. Let's see how this works. One of the top concerns when it comes to declarative migrations comes from experienced Postgres users. And these users asked us about how can they control index creation when creating new indexes. So let's show this with an example. We have our Terraform module here. Here's the data source that's loading the postgres.sql file, and here's the resource that controls the actual database schema. So here we have a simple table to create. We can see that we can create the table. Rerunning Terraform shows us that the schema is already in sync. Now, what happens if we want to create an index? Specifically, let's add a unique index on the username column. So we can see that the plan generated by Atlas is create unique index, which means that this will be a blocking operation. Postgres will wait for the index to be rebuilt before releasing this command. This will be a table lock. The table will be locked for writes, and that's not great when you're doing this in production. So to control this, as we said, Atlas supports something called diff policies. Let's show how this works. So we're going to define a diff policy. We have a policy for concurrent index creation, and we're going to say create true, meaning this is going to instruct Atlas to build this index concurrently to make this an asynchronous, non-blocking operation. In addition, we're going to need to tell Atlas to not run this in a transaction, because you cannot run concurrent index creation in a transaction. So once we do this, our index is created concurrently. Our next invocation is already sync. So there you have it, avoid toll roads, the database edition. The last strategy that I want to share today is something that we call interactive declarative migrations. This is very new for Atlas. In fact, it's so new that it's not yet implemented in the Terraform provider. So we're going to see a demo with the CLI only. And it's very similar to normal declarative migrations, except in certain thresholds, Atlas will open up your browser, with a UI that shows you the migration plan, safety checks that run against this plan, and an inline editor so you can modify the plan if you want. It's not always convenient to have the UI pop up every time that you want to make a change, so you can control in what thresholds Atlas will ask your review. The benefits of this approach, of course, are to avoid unwanted side effects while preserving automatic migration planning and all the benefits of declarative migrations. And it allows you to keep a human in the loop for the edge cases. So you can define policies that most of the time will not ask for your permission for the normal and known cases, but in the edge cases to still have a human review. Let's see how this works. So we have our desired schema here, the Postgres SQL file. I'm going to run Atlas schema apply. And notice that we have three options: apply, lint and edit, and abort. Let's pick lint and apply. This will open our browser. You can see that our migration plan is here. We see that Atlas analyzed the changes and didn't find any issues. And we also have this ERD of representing the change. Let's approve this. Now, we can see the migration logs that ran against the database. Let's go back and make some change. Now let's do a change that is dangerous. It's a destructive change, dropping a column. Again, let's run lint and edit. And you will now see our drop column clause, and you see the change analysis. This is a destructive change, dropping non-virtual column username. And you can see this in the visualization. So let's skip this change. Now, we mentioned that we can control when Atlas asks for our review. So the way to do that is using a lint review error. For example, lint review error means, or let's pick warning. Lint review warning means Atlas will only ask for approval in cases that it finds some diagnostics. So if schema is synced, so we don't need approval, let's make an additive change. This also doesn't need approval since it's completely safe. Changes auto-approved based on lint review policy. But if we were to add a unique constraint, you will see that the changes do require a review. Why? Because these are data-dependent changes. One, it's a non-concurrent index that's going to be created, and adding a unique constraint on an existing column might also fail. In this case, we want to go ahead, so let's approve and see that Atlas successfully ran our migration. Okay, wrapping up. What did we discuss today? We started off by demonstrating the declarative approach for database schema management. We then discussed some of the risks that might deter us from adopting this approach to our production system. And we followed that up with 3 different strategies that allow us to mitigate some of these risks, such as automatic migration planning that lets us review changes during code review and in CI before they're applied. We mentioned diff policies that feed Atlas with considerations and constraints when it is calculating a plan to prevent unwanted side effects to our database. And finally, we demoed interactive declarative migrations, which kind of bake safety policies and human in the loop on edge cases into the declarative migration workflow. Thanks for watching. I hope you enjoy the rest of the conference. And if you have any questions, feel free to ping me on Twitter. Have a good day.